Series parallel circuit problem number 1. In order to work a series parallel circuit, you've got to understand a couple of things. The first thing you need to understand is Ohm's law. You need to know V equals I times R. You need to know R equals V divided by I. And you need to know I equals V divided by R. You also need to understand Kirchoff's voltage law. Kirchoff's voltage law means the sum of the voltage drops in a series circuit will add up to the source voltage. You also need to understand Kirchoff's current law. Kirchoff's current law states the sum of the branch currents in a circuit will add up to the total current. Then you also need to understand that in a series circuit, the current remains the same at every point in a series circuit while the voltage divides. And in a parallel circuit, the voltage drops across parallel resistors remain the same while the current divides. Now, keeping all of that in mind, looking at our circuit, we have a 10-volt source. We have a 1,000, well, actually they're all 1,000 ohm resistors. Now, to work a series parallel circuit, the first thing I'm going to do is ask myself a question. Do I see two resistors in series in this circuit? If the answer is yes, then you're going to combine those resistors and redraw the circuit. If the answer is no, you go to the second question that you'll ask yourself, which is, do I see two resistors in parallel? If the answer to that is yes, then you combine and redraw. If the answer is no, then you go back to the first question, which is, do I see two resistors in series? So we're going to start with the question, do I see two resistors in series? And in this circuit, I do. R1 and R2 are in series. R3 and R4 are in series. R5 and R6 are in series. Now you know how to add up series resistance. You simply add the resistors together. So we'll start with R1 and R2. 1,000 plus 1,000 is 2,000 ohms. R3 and R4, that's also each 1,000, so that would be 2,000. And then R5 and R6 added together would also be 2,000. We now redraw the circuit. We had a 10-volt source. Remember, we combined R1 and R2 together. Oh, I made a mistake. We combined R1 and R2 together and we came up with 2,000 ohms. We then combined R3 and R4 together and came up with 2,000 ohms. And then we combined 4 and 5 together and came up with 2,000 ohms. Now everyone should understand that this 2,000 ohms resistance represents the combination of R1 and R2. This 2,000 ohm resistance represents the combination of R3 and R4. And this 2,000 ohms represents the combination of R4 and R5. Okay. Now we go back to the questions. Do I see two resistors in series in this circuit? The answer is no. So you go to the next question. Do I see two resistors in parallel? And the answer is yes. These two. Now if I take 2,000 and parallel with 2,000, the equivalent resistance will be 1,000 ohms. There's two ways you can do this, or actually three ways. I could use the formula for total resistance, which is this. I would take 2,000 and inverse it. I would add it to 2,000, inverse it, equals, and then inverse the answer, and you'd get 1,000 ohms. Or you could use the formula where the value of the resistor divided by how many there are, and this only works if the resistors are all the same value. Since 2,000 and 2,000 are the same value, I could go 2,000 divided by, and there's two of them, so that would give me 1,000. And then the third formula, I could take resistor 1 times resistor 2 and divide it by resistor 1 plus resistor 2. Okay, I used this one. Since they were the same value, it was the easiest to do. So we combine the 2,000 together, we get an equivalent resistance of 1K, and then you must redraw the circuit. Now I'm going to redraw the circuit. Remember, this equivalent resistance here were the two 2K ohm resistors added together. We come up with 1,000 ohms. And then this was my original R1 and R2 added together, which is 2,000 ohms. Now we ask ourselves the question, do I see two resistors in series? And in this circuit, you do. So RT is going to equal 2K plus 1K. The equivalent resistance for this circuit is 3,000 ohms. Now that I've found the total resistance, I can find the total current for the circuit, I sub T. The formula for total current is the source voltage divided by the total resistance. Since the source voltage is 10 and the total resistance is 3,000 ohms, if I divide those numbers, the answer comes up to 3.33 milliamps. Now I'm going back to the original circuit. We just calculated the total current for the circuit of 3.33 milliamps. Now we know that this is the amount of current that is coming from the battery, going through the circuit and returning to the battery. So right here, I know that I've got 3.3 milliamps of current coming from the battery. What I've got to do is decide, does my current run first into either a resistor or does it run into a node? Well, looking at my circuit, you'll see that this 3.3 milliamps runs into R1 first. So what that tells me is that R1 is a series resistor with the battery. And what do we know about series voltage drops? They must be subtracted from the source voltage. So the first thing I'll do is I'm going to take this 3.3 milliamps and multiply it by the 1K ohm resistor. The K and the milli should cancel out, and you'll end up with 3.33 volts being dropped across R1. Now this 3.33 milliamps, when it leaves R1, where does it go? Does it run into a resistor or does it run into a node? Well, it runs into a resistor, so that's another series resistor. So I've got 3.3 milliamps flowing through R2, and since Ohm's law for voltage is I times R, 3.33 milli times 1K, the K and the milli cancel, so this one also drops 3.33 volts. Now remember Kirchoff's voltage law. The sum of series voltages have to add up to the source voltage. Since R1 and R2 are in series, R1 and R2 are in series with a 10-volt battery, I've got to subtract this voltage and this voltage from the 10 volts. Whatever's left over is going to be the voltage at this node. If I take 10 volts, subtract 3.33 and 3.33, I'll be left over with 3.34 volts at this node. Now think about this for a moment. If I take a voltmeter and place one lead there and one lead down here on ground, I would read 3.34 volts. And what do we know about parallel voltage drops? The voltage remains the same. So if I'm dropping 3.34 volts from this point with respect to ground, what's between this point and ground? I've got R3 and I've got R4. Remember, we combined those together earlier into an equivalent resistance of 2,000 ohms. So if I take this 3.34 volts and divide it by 2,000 ohms, I'll figure out the current flowing down through R3 and R4. .34 volts divided by 2,000 ohms gives you 1.67 milliamps of current. That would be the current flowing through this path. Now remember, R1 and R2 are series resistors. They're in series with the battery. So I've got to subtract these voltages from the 10 volt source. Whatever's left over, 3.34, is left for the rest of the entire circuit. Now I know that R3 and R4 are in parallel with R5 and R6. And we know that parallel voltages remain the same. So if I've got 3.34 volts at this node, then I'm going to have 3.34 volts here. What I'm looking at is, if I took a voltmeter from this point to ground, I would read exactly the same thing on this voltmeter as I'm reading on this voltmeter, because they're in parallel with each other. So there's my 3.34 volts, 3.34 volts. If I take 3.34 volts and divide it by the combination here of 1K and 1K, which is 2,000, as I did here, you'll see that you'll get 1.67 milliamps. 1.67 milliamps. Now, since R3, R4, R5, and R6 are all the same value, that's why this current worked out to be the same in both branches. Okay? Now, the 3.33 milliamps that goes through R1 and R2, when it hits this node, it splits. 1.67 milliamps comes through here, 1.67 milliamps comes through there. They would both recombine on their way back to the battery, and I've got 3.33 milliamps flowing through the circuit again. And it splits, recombines, and back again to go through the circuit. And that pretty much explains all of the voltage drops and all of the branch currents. The only thing left to find would be the power dissipations. And you remember, the one formula for power is the voltage times the current. You can also use voltage squared divided by the resistance. You could also use the current squared times the resistance. So using those three formulas, I can go back and on every resistor, like for R1 for instance, I've got 1K ohm resistor dropping 3.3 volts with 3.3 milliamps flowing through it. As an example, R3 is 1,000 ohms. It has 1.67 milliamps flowing through it. So I can use the I squared R formula to work this one. One thing we didn't do was the voltage drops individually across R3 and R4. I've got 1.67 milliamps through 3 and 4. The 3.3 volts is dropped across the combination R3 and R4. 1,000 times 1.67 milliamps, that's the formula for voltage drop. The milli and the K will cancel, so 1.67 times 1 means this resistor will drop 1.67 volts. R4 is the same value, so it'll also drop 1.67 volts. R5, 1K ohm, 1.67 milliamps, so I'm dropping 1.67 volts there. And R6 is the same value, so I'm dropping 1.67 volts there. Now, what I said at the beginning of the recording about the Kirchoff's laws and about what current and voltage does in a series and parallel circuit, you'll notice here R3 and R4 are in series with each other, so the current stays the same, 1.67 milliamps. R5 and R6 are in series with each other, so the current stays the same, 1.67 milliamps. The voltage divides. I've got 3.34 volts across the series combination of R5 and R6, so that means 3.34 volts must divide between R5 and R6. 1.67 volts plus 1.67 volts equals 3.34 volts. The same is true for this series combination here. Now all of this, the parallel combination of R3, R4, R5, and R6 is actually in series with R1 and R2. So if I was working Kirchoff's voltage law for the entire circuit, I would have to observe the series parallel rules for voltage drops. 3.34 is across this parallel combination. So I would take 3.34 plus the series voltage drop of 3.33 across R2 and 3.33 across R1, and that would equal 10 volts. And that is how you work series parallel circuit number 1.